Thank you very much for the attentions. And then is the next speaker online?
Maybe you can talk with him with Yi-tao. It's online.
Yeah. Hello.
Okay, it's online now.
It's online.
Yes, I'm share my PPT.
Yes. So the next speaker is the Dr. Yi-tao Long. No.
Yeah.
Yes, and then the presentation title is NANOPORE electrochemistry for single molecule analysis. So please start it.
Oh, thank you. Thank you for the organizing for Twitter and cooking invitation for me to give my research presentation on my about 30 years research. And also it's a long talk. It's not only for me and also for my supervisor, Professor Chen, because he's farmer in China in research in analytical area. See, we got the 2015, we got nature most award for contribution for the young scientists in China in our world, and also Professor putting model is in hologram, and that's about 20 years ago in China with all the well-known chemistry in the world. Many universities in the US for the shop. He's in analytical chemistry, so this is a very traumatic memory for me to remember that. And I'm training in this university for 20 years ago, and now I'm chemical science associate editor. So this journal is Royal Society Chemistry in UK. It's a flagship journal to publish all area research in chemistry. So I'm handling the manuscript from the electrochemistry and sensing. So this is a great journal, and I'm welcome for also to support this journal and do submission for this journal. Thank you. And back to my research career, I'm grew up in very small town, but a very old town in China. It's a central China called Pei town. And when I go to university, it's Shandong University. It's very north in China. After my training in battery, I went to Nanjing University to do my master and PhD with Professor Chen Hongyan. And after got my PhD, I went to Germany in Heidelberg and with Michel Grunz to study the surface science for 2 years. Then I get a short time in Paris, in Symp, and then went to Canada for 4 years. It's a very cool country, but it's very beautiful country too. Before I back to China, I worked with Gabor Samjai in Berkeley for the surface science. So I stay in Shanghai for my independent research about 12 years. Then I went back to my home university, Nanjing University. But now Nanjing University location is from Gulou to the Xianing. So in the world, I travel around circle, which is very important for my research. I will presenting this circle in my presentations. So my research career in chemistry is starting from Professor Chen. That time, we studied the electrochemistry reaction on the silver electrode. See, this NADH is a kind of enzyme. It's also coenzyme stuff. And we studied that just for the concentration, because that time we understanding the electrode only the like a one-dimensional electrode. It's everywhere in the electrode is the same. So this metal electrode to study the NADH reduction or oxidation on the surface. Then we glue some more layer on the surface. So we're extending the surface to the two-dimensional surface for the sensing, because the molecular modified on the surface, they were sensing the target molecule. So this called the chemical modified interface. So any molecule that if can locate it on the surface, but still can move around on the surface, we put the bilipid on the surface. So the bilipid is kind of a moment substrate. So the coenzyme can insert to the membrane, can move around like coenzyme 10 and coenzyme NADH. So they can electric catalysis the analyte. So we call it the three-dimensional space. This confined biomolecular environment. So this we call three-dimensional surface. So right now we study the nanopore, which is the channel stick on the surface. So analyte can pass through this channel, can like with the time. So we add the time dimensional, we call four-dimensional interface. So this can study the single molecular component surface. We call this one. So this around 30 years, which I'm studying on the focus on the electrochemistry step one by step. So that's my academic career for the 30 years. So this is my group. When I back to Nanjing about 5 years. So this is my group members. I thank all the students and the colleagues with me as they share the time and research. So this is my research interest in China. So one is the electrochemical optical single entity, and also the nanopore electrochemistry and the instrumentation I will take you in my talk. So back to the research for the sensing. You see this is a C, very nice C. Everybody can see that. But when we want to test the salt in the C, we need to take the sample in the beak. So we will heat the solution and get the salt. Then we will wait that when we know the concentration of the salt. So that means take the sample and wait. That means confine the sample here. If you want to see some bacteria in the water, we need to use a microscope. So we also need to reduce the concentration, reduce space. So we'll look at this area to use a microscope. If you want to see one bacteria, we need some special tool to take like AFM to reduce the tools down to the confinement to the single molecule space. So that's all things for the measurement, for the sensing. It's all confinement for the measurement. So in 1995, or 1996, so let's say this science paper from Aaron Barber, he reduced this space down to the very smaller than to measure single molecular electrochemistry in this space, in this very tiny space. That's confinement to push the limitation. And also in 1996, they used one protein channel to make this small space to measure the single strand of DNA to sequence it. This all use the nano confinement concept, I think. So I am focused on this study because this is electrochemistry measurement. Why? Because this is two electrodes separated by one thin lipid layer. This thin layer is 3 to 5 nanometer thickness. So there will no current pass through this. If this put in a solution, no current pass through. So there's a zero current. One single protein channel, like protein pore, insert to the bilayer, they will open this circle. So we can measure the undercurrent because the pore in diameter is very small. It's 1 nanometer. So sunlight will be driven by electrical force to pass through this channel to get the analyte events for the individual molecule because of the channel size very smaller, and also the molecular pass through is very fast. We need a high throughput, high bandwidth implementations, because this technique is labor-free and high throughput and in situ detection. So this is very powerful technique for single molecule detections. When we use the electrochemistry concept of understanding this technique, we'll see 100 millivolts potential applied to this bilayer. About 99% of the potential will drive into the high resistance here. So we can ignore the resistor in the solution. That's why we need a high bandwidth and ultra lower current measurement to get the tiny signal. And also we need the nanopore material to extending these techniques. So let's the nanopore resistors model tell us. So back to the traditional sensing surface. We use, like we talked about before, we use the chemical modified surface. We put a different molecule or same molecule on the surface as sensing to target molecule here, but we cannot control this target molecule to interaction with this one or this one. And also we cannot control the time sequence about that. That's the weakness of the micro interface or senses. When we think about, can we make a single molecular surface? So let's like plant the surface. We turn around, make a channel. There will be nanopore interface because this surface is well-defined interface and the time and with the time series. So we call this a single bimolecular interface. We call this one because in the natural system we have nose and ear. All this channel or this channel shape. All those signal it's for the sensing the molecular or sensing the sound. So this sensing sense. So nature tells us channel can make something can amplify the signal. So this is for example, this is a protein nanopore called R-lysine, which is 1 nanometer for the channel diameters and 10 nanometer for the length, for the thickness. So this we call this space is the confined space here. So this is the cryo-EM imaging we got just recently. So we know exactly the amino acids in which location. You listen by protein pore, we measure the polyethylene for different lengths. So with our naked eye, we can see the mixture sample of those shorter DNA. We can see that's the events here, and also we can determine in the mixture sample we can tell which peak is corresponding to the short DNAs. We use this technique can determine the real time the enzyme digestions, because the enzyme can shorten DNA the sequence one by one, so we can measure the enzyme activities in situ. And turn to the nanopore structure here, because it's 10 nanometer length and 1 nanometer in a channel. So this is the controllable genetically can design the amino acids here. When we open this channel, like the surface, each of the reaction site, we can play with the genetic any genetic engineering to modify the modify the amino acids here. This is reaction 1, reaction site 2, reaction site 3, 4. And unlike pass through this channel, they will have time serial interaction with each of the site. That's the important understanding for design the channel, also for design the proteins here. So back to the electrochemical understanding, we use the equivalent resistance model for the nanopore. We see this is the current from the solution. This is the resistor from the nanopore of the proteins. So each of the amino acids here, we think is one resistors with different volumes, and also this we call this three-dimensional confined space. Also, the chemical group make the resistors difference. So this is a variable resistors in a series. So when analyte pass through this channel, that means we measure the series resistors by the electrochemical instrumentations. So we can get the current print for each single molecule. So let's can get that will be identify the single molecule. So that's the background theoretical understanding for the nanopore so far. We understanding this one is not only for the volume changes for the solution. We think interaction is very important. Interaction contribution will be nearly to 90s, and volume and mass difference will be contributing the current down to the 10%, which is like the key and the ball and the lock. So the spring will be like the amino acids interactions between the teeth and the keys. So with this understanding, we wrote a paper, but it's hard to publish that. We try because they don't like chemistry subjects. So this is the current. We think it's the volume and the interactions together. So we new site, this new insight for the nanopore confinement understanding. So that will be open a new world for the nanopore study. With this understanding, the application is with sensing nucleotide, like I talked before, and also we sensing the transistor conformation of some coenzyme like FAD, and also we can quantify the damaged DNA, and also simultaneously to study the dephosphorylations of DNA, which is only one DNA basis changes by the phosphate or sulfate. So we can mapping the adjacent phosphate site, which means in a whole chance of this peptides, we can only one of the peptides be phosphorylations. We can determine that in which location in the peptides. So that means we can enhance the electrical static interactions, because we change we engineering the protein core by single amino acids residue. So that's why we can measure you see this in this phosphorylation in this portion or this portion, they will tell us by the nanopore techniques. And also because this technique is a level-free measurement, so we can measure in the mixture of the peptide system. We can sense in the peptides like mass spec even. You see this peak very sharp, and the content we can tell only one amino acids difference. And back to the understanding what's the behind in the current here, current signal here. When the analyte pass through this channel, there will interaction with each amino acids. We use one-by interactions, electrical interactions, and hydrogen bonding interactions. So all those information will harden in this current signals here. So we use the so this is the noise, and all noise is energies. So we use the time domain to convert to the frequency domain. We use the Harper-Wang transform, and we will get the single molecular interaction spectrum. So we can build up interactions spectral library to tell us the hydrogen bonding and van der Waals force, and even for the electrostatic force for each amino acids here. So this is called the interaction network by the ionic ions and the analyte and the channel. So we can convolute these interactions. So in the confined space, we call this a single molecule. Why? Because we play with the keyboard, which is the amino acids in the channel, and all the analyte like the node pass through this channel. So that's like the traditional music in France. So we can play with the single molecular music. So science also music, I think. And this is the site one amino acid changes use the metagenetic technique. So this is this is negative amino acids, positive amino acids, hydrophobic and hydrophilic. So we can play with like play with the keyboard of the music. So that's why we call this single molecular music. So back to the nature, we have 20 amino acids in the world to build our body and all the world, the animal and plants. So we can see I play with this 20 natural amino acids, use a table. So they were published in the ongoing chemistry. So because we think they have some understanding theory behind these amino acids. So we think this period table, like elemental period table, is amino acid table. Which is this is negative charged amino acids, and this positive charged amino acids, and some is non-charged but hydrophobic and hydrophilic. So we can understand this one. We can play with the design the multi-domain nanopore for identification, because non-covalent interactions, which is electrical static repel and anti-reactions and hydrogen bondings, and for the dynamic covalent interactions, which is sulfur and amino sulfur. And for the energy bursts, we can build up the larger amino acid residue in the channel to make this shape difference. And also we can play with unsymmetrical environments, which is hotter nanopores. It's just one, because these nanopores formed by 6 same strand of peptides. So we can change one peptides to make it unsymmetrical nanopores. So with this understanding, we can determine the theory molecule like lucent, this D shape and the L shape, we can enhance the space resolutions for the molecular recognitions. And this is one of my small dream to make a protein nanopore sequence by instrumentations and achieve the identified the sequence even for the post translations modifications and also for the conformations of individual proteins. Recently, I just got Friday IC Friday metals because Friday is my give me a lot of inspirations in my research area. So he tells us one very famous quotation here: "Nothing is too wonderful to be true if it be consistent with the laws of nature." And also very important, in such things, a low experimental is the best test of such consistency. I like this man, and also because not only for his own education at his young ages, he's become the greatest chemist in the world so far, I think. And my career in Canada is very special because I'm staying in the winter time. It's down to the -40 centigrade and high fight because the same values there always in the winter time. Because we know this is my proposal in Canada. Because somebody already did the DNA, I want to try the peptide sequence, but at that time I cannot get the funding, and the proposal failed because their understanding that time it's a DNA century dogma already tell us, because the DNA sequence already can tell us the amino acid sequence. So we don't need to do with the century dogma. We don't need to do it's nothing for the peptide sequence. But now difference. I still focused on this peptide detection of peptide sequence. When back to China, that's the first paper published in Chemical Asian Journal. I think peptide nanopore study the peptide is the future. In the COVID-19 season, I grabbed with Hagen Bailey in Oxford and Siddhartha in Holland and Amino Miller in Technon. We wrote a paper to beyond the DNA sequence. Now the protein sequence and protein structure and biomarker identification in nanopore is very popular. And also we are studying the single molecular chemistry in the channel, even for biomimic systems. Let's tell something news. This is the single amino acid discriminations with to study the COVID-19 SAE2 detections with agents. Also, we studied a single peptide sequence and sensing the amino acids, even the amino acid serial. This for the D and the S shape. And also we studied the family point mutations for beta amyloids peptides, and we use unnatural amino acid modified in the channel. We can measure even more peptides here. With measure those signal, we need to develop the instrumentations. Here it's the instrumentations we developed for 20 years, starting from 2010s. We use one generations. My supervisor, Professor Hong Yan Chen, always challenged me in China. See, when I back China, he went to my lab in Shanghai and even each year and give us lots, even supervisions and suggestions. Also, a Nobel Prize honor start with us because he liked us very much for the research. He think our nanopore is kind of molecular machines. we use this technique, we can reading high resolution electrochemical signals. Our chemist young students developed this electrical cycle and make the successful implementations. So let's maybe you can see he can sort something even more familiar compare the techniques of training by the schools. See, in one word, I can make this technique more simple, more reliable to be used. Even we publish the Nature protocols to make this technique down to my graduate students can handle this technique easily, and also I can use a higher equity to use the high potential to use the called collaborations for these high band measurements. So we can know which data is correct, which instrumentation is correct. So all this be quality controlled in the laboratory. And we use the different software to recording the signals and save the signal, analyze the signals. That's why I think this technique can done to the undergrad students class. So we spend 4 years to training different ages undergrad students that can handle this technique in one afternoon. So all the data can be repeatable, and we published one paper in the journal of education, chemical educations. So to training undergrad students to understanding single molecule analyze and the detections and also implementations. This is a complementary training for student. I love this teaching. So this is not in a limited class can get unlimited understanding knowledges. So I'll give a very short conclusions here. This is geometrical space should class the time series energy, that means confinement. Down to the nanoscale, the energies come from the chemical bond, chemical groups and the interactions. I want to skip this one because this is not so important for us this time, because I use the understanding to measure something the liquid solution in a vacuum, because we understanding that the nanopore is kind of confinement spaceship. So we can measure the ionic, even the solution in a vacuum system. So this is my 20 years study for nanopore. The measurement, we measure the DNA, protein. We get a new knowledge to get the hiding the knowledge, hiding the information down to the in the current, and some applications for single molecular synthesis and single molecular sequence here. Nanopore become a word is very popular with the Web of Science. Our publications influence is the first in our the research groups. And also we holding a nanopore weekly meeting every week, every Monday night for 5 years, even for 4 years already. So it's continually to training the young students to be in this area. So welcome to be our meetings. And I need to talk about my friend here, because the Friday is kind of very important. It's 2016. It's a single entity electrochemistry, and this is a great event for us. So I will study this one for continually. So let's because it's a serious meeting, and the next meeting in China will be 2024. Just give me maybe. Oh, sorry. Let me. I still have 10 minutes. I think, right? I'm sorry. I think I still have 10 minutes. So I welcome you to visit us and attending this Friday discussion, because this 5 minutes talk and 25 minutes questions, this give us a very deeply discussions. I need to tell about something, but it's related to my talk. So this is a very traditional place you need to see, because this is called Jinsa Museum. They get the gold mask for even for 5,000 years ago. And also this is very special, the sun called the sun and birds falling, because this it's about 12 centimeter this size, this shape, and 20 micrometers for the thickness. Can you imagine for 5,000 years ago, people can make this one in China? Let's take this photo taken by me. So this look at this one is 12 of the different exactly the shape inside here is a circle, right? And also everybody know that, because everybody wants that. It's Jada ring, and this is very old Jada B desk, because the ring is smaller. And also this is the Jada ring, because the thickness is huge, and different. That's 4. Let's call it 10. This is called 10 note. This is called 4 notes. 1, 2, 3, 4. So this inside is a circle, is round shape. And this all those one is round, right? It's all round shape. But it's different, right? But when you see this is eye, this is look, this is see, all those looks like we will tell this like a man, this like a face. So this is me, okay. And unless my question is English is language as hieroglyphics. Maybe you disagree. But when you look at the mountain here, it's a mountain word in China, in Chinese writing. And it's all Chinese writing here, but it's mountain in English, right? So when we take a look at this shape, we will see this one, and take this shape is also then. This is called, in China, it's called sun, but in English, it's called mountain. The different pronunciations, but here is the same pronunciations in China and in English. Here, let's see, we call this one is Hao, because this in China, in English, is Hao, same words. Hollow and how, I think in English is happy is great, and in China also the same meaning, and health is it's same meaning in Chinese. So hollow and holy, honor is all same meaning Chinese. So why that? Because you see the letter A. Letter A it looks like a tug. It's angry. It's the angle is it's against attention. It's even acid, because acid is tug my tongues. So this is A. And go off, because this you should have breath. You should use the tug. You can climb here. And for the C, because C is a cell, C is cut. Also, this is not my conclusion here. This is because the book tells us this. When you have interest, you can look at the book. The book tells you everything, every word in Chinese and in English. So before I'm close my talk, I think this is a quotation influenced me, because quotation in the University of Birmingham, that's on the wall. They call it to seek, to travel, to seek, and to find, and not be heard. This is my research. So thank you very much for your attention. Welcome to China. Thank you very much for giving me this chance to presenting my academic philosophy here. Thank you very much. Thank you for organizing.